Good evening, colleagues and guests, and welcome to this wonderful lecture theatre and to the Lorna Casselton Memorial Lecture. I'm Cassie from the Masters in Cross College, and it's a tremendous honour and pleasure to be with you here this evening. This lecture series is established in the name of one of our fellows, Honorary Fellows, Lorna Casselton, who was a very well-renowned fungal science geneticist whose work with the Royal Society as Foreign Secretary reached out to international science communities. And one of the ways in which we felt it would be very appropriate to remember her, thanks to the generosity of those very many people who donated to make this possible, was to have a series of lectures that would bring international scientists to Oxford to share their knowledge, their excitement and their passion for what they did. And we're delighted that many of Lorna's family and friends are with us this evening, and we hope that they will continue to be proud of this lecture series and feel that it's an appropriate way of honouring her memory. Tonight we are extremely excited. We have Dr. Stofan with us, who until very recently was NASA's chief scientist and is now working with Johns Hopkins University and planning all sorts of projects. Now, Ellen is a planetary geologist whose father was a rocket scientist and who saw her first launch at the age of 4, which is pretty spectacular going, really, to be that excited at that age by something that goes on to be your passion and your scientific area of work. Added to the interest in rockets and space and science, Ellen then went on a geology field trip with her mother at the age of 12 and decided not long after that there was a wonderful combination here to be garnered, which was rockets and science and space and geology, hence planetary geology. So we are absolutely delighted that she's here with us this evening to talk about the international search for life beyond Earth and all of the projects that she's been involved in. I think it might be a bit much to expect an alien in the pocket, but we're very, very hopeful of some fascinating insights. So Ellen, please, take it.
Thank you very, very much. It's really an honor to be here and to be giving this lecture in honor of Lorna Casselton. I'm really pleased to be here tonight. And I hope to be able to give you some sense of the excitement, because we are truly living in a unique time period in terms of trying to determine if there is life beyond Earth. We know, I hope I'm going to convince you, we know where to go, we know what to measure, and probably, and I'll get into that, and we have the technology to make these measurements. So we really do live in amazing times. It's funny telling that story because about my childhood, which I always say that's that first launch I went to when I was 4, the rocket actually exploded on the launch pad. Luckily it was an uncrewed launch, but I always say that's probably why I never wanted to be an astronaut. But what was amazing to me after figuring out there was this thing called geology where you could look at rocks, and I had picked up rocks since I was a kid, and so I went with this geologist on this field trip, and I'm like, people get paid to pick up rocks. This is amazing. I didn't know they had such a thing. But what really inspired me to go into this field is this very question that we're talking about tonight. Because when I was about 14, my father was in charge of the rockets that were launching the first two landers to Mars, the Viking landers. And I was a kid, and we kind of hung out with all the other NASA kids. None of the NASA kids if you were from one center versus another, there's all these factions amongst the kids. But we got to go to these talks by the scientists from the mission. And there was this one guy who was talking about why we were going to Mars, this search for water, ultimately trying to find this Earth-like planet to better understand our own. He was this guy named Carl Sagan. And at that point, I said, wow, that sounds like a pretty interesting career. I think I'll do that. Now, as we, fast forward to the current day, this question that we have, are we alone? Is there life beyond Earth? You might think, oh, is that something that's just wondered about in the popular press? But when you go back and say, how do the space agencies of the world, how does NASA actually decide what its priorities are? How does it decide what to go, where to go, what to measure? In the US, we actually have a system through our National Academies of Science where we put together what are called decadal surveys. So we bring the scientific community together and they sort of put together a 10-year strategic plan. It's a very open process, and increasingly we're trying to figure out how do we get the whole international community. And everything I'm going to be talking about tonight, all the science I'm going to be talking about, was not just accomplished by scientists from the United States, because every mission I'm going to be talking about, every result I'm going to be talking about, in general was done by an international team of scientists. Basically, every NASA mission in general these days has European instruments on it, or maybe Japanese instruments. And similarly, many missions from the European Space Agency have US participation. So it's truly an international scientific community, and that's how we study things. But in these decadal surveys, which are done for heliophysics, astrophysics, planetary science, and earth science, there's always this beginning that says, what are the driving questions that these scientific disciplines are trying to answer? And that search for life is always part of them. But all those questions always also come back to what I sort of summarize as origins and evolution. Where did the universe come from and how has it changed over time? How do planetary systems form? How do they evolve? How do planets form? And ultimately, obviously, our question is, how do you get an Earth-like planet? How do you get a habitable planet? How did the Earth become habitable? Why has it stayed habitable? What is the future fate? And so those are sort of the underlying questions that actually, if you read the introductions to all of those decadal surveys, they're going to reflect those sorts of questions. This is, obviously one of the most iconic images that was returned from the Hubble Space Telescope, which is 26 years old this year, 26 or 27. It's older than several of my children, which is very strange. But this is the Hubble, for those who don't know, this is called the Hubble Deep Field image, where they pointed Hubble at a very dark part of the sky. They just collected light, collected light, collected light. So what you're seeing is a time about 500 million years or so after the Big Bang. So this is the very, very early universe. And I love this image, first of all, because I think it's really pretty. But it's also amazing because of the complexity that you see. In the very early universe, you had incredible complexity. All those points of light are not stars, they're galaxies. And so this sort of confirms, there's something called the Drake equation, whereas we start wondering, how do you decide if there's life beyond Earth? How are we going to determine the likelihood of life beyond Earth? So the scientist Frank Drake put together this equation. And one of the terms in the equation is actually how many stars are there, how many planets are there? And what we've certainly learned from Hubble, from all of our orbiting telescopes, is there are a lot of galaxies, and all of those galaxies have a lot of stars in them. And so when we start saying, okay, what's the playing field? When we start thinking about life beyond Earth, we certainly know there's a lot of stars out there to start searching for life. And that complexity actually occurred fairly early on. Now, about 10 years ago, I was writing a book for National Geographic on comparative planetology with a friend of mine who is an astronaut. And he was writing the chapter on extrasolar planets. And again, this was about 2007 or so. And as he was writing this chapter, he kept having to revise it because new planets were being discovered every month. But at that point, most of the planets that we were discovering were quite large because that's what we had the technology to be able to detect. And in general, they were quite close to their parent star. So very hot, sort of hot Jupiters were what was a lot of the extrasolar planets that had been discovered. Then about 4 years ago, NASA launched the Kepler Space Telescope. Kepler to date has found over 2,500 confirmed planets in an area of the sky that if you went out tonight and held up a couple of your fingers, you'd be blocking out the area of the night sky that Kepler was looking at. So in a very small area of stars in our galaxy, over 2,500 planets. And not just single planets around stars, but 3 planet systems, 5 planet systems, 7 planet systems. So we believe that what Kepler is telling us is that almost every star that you see is likely to have a planetary system around it. So now back to the Drake equation. Okay, there's lots of stars, and now there's lots and lots and lots of planets. So we're starting to get somewhere. Now, the other good thing about Kepler is it actually had the ability to detect relatively small planets, the size of, basically between the size of Earth and Neptune. And we think that that size planet is likely to be able to hold onto an atmosphere. And thus, all of a sudden, again, looking for that Earth 2.0, the probability of finding other Earths seems to go up. Now, what we're really looking for, though, is a planet in what we call the habitable zone. So that's the distance from a parent star where water is likely to be present on the surface. Now, why water? Well, obviously, we live on a water planet. We know that life here on Earth evolved in the oceans, and it remained in the oceans for over 1 billion years. We think that water is important to the formation of life. Water is a solvent. So it is a fluid, so lots of things dissolve in it. You can have nutrients that a cell can use. It's a fluid medium, so you can bring in nutrients and take out waste. There's all kinds of things about water that we think are important to life. But always in the back of your mind, you have to keep a little skeptical thought there and say, we're doing really well with our one data point and understanding our one data point, and we love our one data point, but it's one data point. And that's all we have. So when we search for life beyond Earth, we're looking for life that follows a model of what we know based on this planet. In general, in planetary science, what we found is when we base things only on the Earth, we're generally not entirely right. So I'm actually optimistic, and I'll get to this later, that life is going to be a lot stranger than just needing to be in the habitable zone, but I'll get to that eventually. So again, we're sort of looking for this situation, a planet distant from its parent star where water is stable on the surface. Now, we've started to find planets in the habitable zone. This is an artist's depiction, obviously, of a new system that was just discovered about a month or so ago. It's a star called Trappist 1. And a 7-planet system was discovered around it using both Earth-based and space-based telescopes. And as you can see from the depiction there, several of the planets actually sit in an area where water could be liquid on the surface. Now, just saying, all right, they're the right distance from the parent star, we understand how bright the star is, we understand the distance of the planet, its size. That doesn't mean there is water on the surface. It doesn't even mean the planet has an atmosphere. We don't know that. All we know is it's about in the right place. From the Kepler Space Telescope, we actually now have a fairly, basically under 10, but we still have a significant number now of planets, and they're actually being discovered now by ground-based telescopes all the time, a significant number of growing candidates of these planets that sit in the habitable zone. In the next about 2 to 3 years, there's going to be 2 more telescopes that are going to be launched. A U.S. mission called TESS, the Transiting Exoplanet Survey Satellite, and CHEOPS, which is a European mission. Both of those are going to continue this search for planets around other stars, and it's estimated that TESS will actually find a planet in the habitable zone about once a month over its 3-year mission. So that'll be at least 36 more of these planets that sit in the habitable zone. But the astrobiology community is really trying to understand, okay, water on the surface, right distance from a star, is that really the whole picture? Of course not. It's way more complicated than this. And this is one scientist in the US, Vicki Meadows, who's just sort of started a chart of saying, okay, what are all the factors that actually play into habitability besides just having liquid water on the surface. And of course, it's incredibly more complicated. What are the dynamics of the planet? What's the atmosphere of the planet? Does the planet have a magnetic field that protects the planet from radiation from galactic cosmic rays and from radiation, coming from its parent star? Does it have plate tectonics like here on the Earth? How does tectonics actually influence life? These are huge questions that we really don't understand the answer to, of why did life here evolve here on Earth? How important are all of these various factors? So how do you get a habitable planet? And the scientific community is really trying to pull apart all of the threads of this to understand just being the right distance from a parent star isn't enough. It's more complicated than that. It's even more complicated than that in terms of, are you looking at that planet in the right point in its evolution when it's habitable? Because the habitable zone actually isn't just a place, it can be a time. Any of these could have been, has been the Earth at some point in its history. At some point very early in the Earth's history, up there in the upper left, the Earth actually had a magma ocean. Its surface was basically liquid lava across the surface. So if we're observing a planetary system around another star, and we're observing it very early in the evolution of those planets, we may not catch that planet when it's habitable. It's too young. It's very early in its formation stage. We could catch it at a point in its evolution that people have theorized from the Earth called Snowball Earth, when the Earth is actually largely covered by ice. So finding that nice habitable Earth that we live on right now is an added factor of complexity. Again, habitable zone isn't just a place, it's also a time in the history of a planet. So how are we moving forward on this beyond the two missions I've already talked about? Well, the big focus in the US over the last several years has been around this telescope. It's called the James Webb Space Telescope. It's truly an amazing telescope. It's going to launch in about a year. It's going to be placed out at L2, which is one of the Lagrange points, where you have a stable place to put objects. We try to get it away from the Earth because the Earth puts out all this light, and you want telescopes to look at very faint objects very deep in the universe, so they need basically sunlight and Earth-like blocked out. What you can't see here, and this actually has one of the mirror segments folded back, is James Webb has these elaborate sunshades that it points at the sun to block out the majority of the sun's light. James Webb will actually look at the atmospheres of a handful of these planets that sit in habitable zones. All right, so now we'll not just know it's in the right place, but we'll be able to start asking questions about, does it have gases that we associate with life here on Earth? Oxygen, carbon dioxide, methane. And we'll be able to say, to start to try to determine, are those gases in equilibrium? Or do we see disequilibrium that might indicate there's an active process going on that planet? Now, for example, on Titan, which is Saturn's moon that I'm going to talk about in a little bit, there's disequilibria in Titan's atmosphere, but it's caused by geologic processes, not by biological ones. So just because you find disequilibria doesn't mean the active process is life, but at least it gives you a starting point to ask further questions. So that's what we're going to start doing with James Webb. James Webb has been being tested at the Goddard Space Flight Center in Maryland. It's being shipped right now to the Johnson Space Center in Texas because it was the only place that NASA had a big enough thermal vacuum chamber to have it go through its final thermal testing. And it's truly an amazing chamber. The door on the chamber is about as tall as the wall behind me, and they used the chamber to test the Apollo capsule. So it's this really amazing facility. It actually hadn't been used in years, and they've refurbished it to test the James Webb Space Telescope. The telescope then goes out to California, where it gets final putting together. And then my favorite part of it is they actually put the telescope on a boat because it's too big. It's launching on an Ariane rocket out of French Guiana. And so they have to put it on a boat in California, and it actually goes through the Panama Canal, which I would love to go see, because here you have this amazing miracle of technology going through what at the time was an amazing feat of humanity, and they're going to be juxtaposed right against each other. So we're really looking forward to the launch of James Webb, and again, part of it is it's going to move us this next step forward in trying to understand extrasolar planets. When you think, okay, but what's the next step? And what I forgot to mention was one of the things with James Webb is you could see on that one panel of mirrors is actually folded back there on the right side. James Webb is so big that it has to be folded up to fit in the fairing. The fairing is the top part of the rocket, and so you have to fit inside those. Those only come in standard sizes, believe it or not, and you have to be able to fit in there to be launched off the surface of the Earth. So James Webb actually folds all up. That other mirror segment on the side folds around. The sunshade is all folded up. Its solar panels are folded up, and it actually takes about a week to do all the deployments on James Webb. And they all have to work because, for example, if the sunshade doesn't deploy, there'll be too much light let into the telescope. We won't be able to get good data. So all of these deployments are really critical, and everybody laughs because when you land on Mars, people say, oh, it's 7 minutes of terror because it takes you 7 minutes to get from the top of the atmosphere to the bottom, and you hope everything works. With James Webb, this is going to be a week of terror as all of these things slowly unfold. But obviously, that's really no way to do business, is folding your telescope up into a little origami shape. Ultimately, if we want to image one of these planets around other stars, we need a much larger aperture telescope, 10 meters, 15 meters, 20-meter telescope. You can't fold those up enough to launch them, so we're actually going to have to construct them in space. So right now, on both sides of the Atlantic, studies have been going underway trying to say, how do we build that next telescope? How do we build that next generation telescope that wouldn't launch until beyond 2030, and maybe even later, that will be this much larger aperture telescope that can actually image planets around other stars. So unfortunately, while there's technology studies going on, we're just not there yet. We actually have one of my favorite programs at NASA is a program called NIAC, which stands for NASA Innovative Advanced Concepts. And so if you're ever bored, you should go to the NIAC webpage because people don't like it when I say this, but it's where we test out wacky ideas. And you'd like to say, of course, we don't spend money on wacky ideas. That would be a waste of taxpayer money. But how do you get to that technology that's truly groundbreaking? What's the difference between a wacky idea and an idea that's going to change how you collect data or build spacecraft or make a measurement? So NIAC is a way that we can fund really cool advanced concepts. And one of the concepts that I loved on NIAC was spacecrafts that would basically act like a series of spiders and spin basically a large substructure that would hold all the mirrors for a very large space telescope. So there's also like submarines on NIAC studies. So again, if you're bored, go look at the NIAC website. So all of this discussion of extrasolar planets, looking for habitable planets, looking for life beyond Earth, makes us really come back to our own solar system and say, okay, if we really want to start thinking even more about the Drake equation, what is the likelihood of life beyond Earth? Why is the Earth the only place so far in this solar system where we've found evidence of life? Are there other places in this solar system where you could say, if the conditions were more or less like the conditions on the early Earth, if we had those key ingredients for life, did life evolve only here on Earth, or could it have evolved in other locations? So we start to look at our own solar system, and obviously this is not to scale, and we start saying, all right, what about the planets in the habitable zone here in our own solar system? What's the story with that? Are there opportunities for life beyond the habitable zone that's actually going to make everything I've just talked about not as important? And the answer to that is also yes. And so I'm going to talk about two broad categories that we've been looking for, trying to understand habitability. The first are the planets of the inner solar system, and then the moons of the outer solar system. So when I talked about habitability being just not a place but a time, that was definitely true in this solar system. So if you look at Venus, Earth, and Mars, all of those planets at one time were potentially habitable. If you go back to the question of saying, what is habitability defined of? Well, we're going to start with water on the surface of the planet. So Venus, we know, and I've spent most of my career working on the geology of Venus. It's the unloved, unstudied planet that we need to learn more about, because Venus really is Earth's evil twin. You know, you really did start with basically the same ingredients as the Earth. It's made of about the same stuff. It's about the same size as the Earth. It's really, relative to the Sun, about the same place in the solar system. But Venus has gone down this extremely different trajectory. It obviously has a runaway greenhouse atmosphere, extremely hot on the surface, a surface that's now dominated by volcanism, and maybe by some strange overturns of its interior that give massive outpourings of volcanism on its surface. Certainly not habitable by the standards that we think about, though I have a colleague named David Grinspoon who's talked about maybe life in the clouds of Venus, but we're not going to go there. So what we know from isotopic measurements that have been made of Venus's atmosphere is that Venus, early in its history, is likely to have lost an ocean's worth of water. So it's very conceivable that in Venus's first, billion years or so, it had an ocean's worth of water on its surface. Now, why did it lose that ocean? Was there actually a liquid water ocean on the surface? Was the water in some other form? We don't know. We need more data, which is why we keep proposing missions to Venus and they keep not getting selected. And Colin Wilson and I, who's here at Oxford, he and I have been on some of those losing proposals, but Colin's doing better now, so hopefully his will go forward. So fascinating basic questions about Venus. Was it actually ever habitable? How long did those conditions last? These are questions that we actually know how to go determine on Venus. There's measurements we need to make in the atmosphere. There's measurements we need to make on the surface to actually pin this down and help us understand, okay, again, here's a planet in the habitable zone. It went south. The Earth went habitable. Why? We don't know. Mars, of course, as many of you know, has been a huge focus of exploration by all of the international space agencies. And in fact, the theme for Mars exploration has been follow the water. What is the history of water on the red planet? And what we've learned, and I'll come back to this in a minute, is that water was stable on Mars's surface for on the order of 1 billion years, maybe a little less, about 3 to 4 billion years ago. Now, the second thing besides water that's important, you should say, well, you need something for life to be made out of, right? Organic molecules is what we're made out of. And why I haven't brought those up is actually that's the easy part. We have found amino acids in meteorites, so they're in asteroids. We've found amino acids in interstellar clouds. We've found them in comets. So the building blocks of life, those organic molecules, have been delivered all over the solar system. Now, did they combine in a way that then advanced towards life? That's the hard part, but those building blocks of life were spread all over. So again, you have to say, if Venus had an early ocean, if Mars had an early ocean around the same time the Earth did, shouldn't life have also evolved there, given that life evolved very rapidly here on this planet once conditions stabilized? Now, all this talk about the habitable zone is complicated by the fact that part of my planetary science community is going to argue with you that the best place to find life beyond Earth isn't in the habitable zone in our solar system at all. It's at one of these worlds out in the outer solar system, one of the icy moons of Jupiter or Saturn. Because what we know, and put Titan aside, and I'll come back to Titan in a little bit, what we know about Europa, Enceladus, Callisto, Ganymede, and probably Triton is these bodies way out in the solar system, again, they're moons, they're dominantly made of water ice. They have a small component of rock that forms a rocky core of the body. The ice is basically the crust. It's extremely cold out in the outer solar system. So when I talk about water ice that makes up the crust of these planets, think of it as behaving like rock. It's on the order of, say, 90, 100 Kelvin out at these bodies. So ice is rock, water ice is rock at those temperatures. But beneath the icy crust of these planets, of these little moons, are actually liquid water oceans. Now why? Well, the ice has melted. Why is the ice melted? Well, it turns out in general, all of these satellites are being pulled on by their parent giant planet, whether it's Jupiter or Saturn. So as these, remember, Jupiter and Saturn are incredibly massive. As these moons orbit around these massive bodies, the giant planet is tugging on them. So as they go through their orbit, it actually causes frictional heating of their interiors, which melts, it creates a lot of heat, and that melts the, we think the rock in their interiors as well as some of the water ice, forming this liquid water ocean under those surfaces. And we've gotten that information that these oceans are there from satellites like Galileo and like Cassini that have gone out and studied these systems. So, okay, you have water oceans. There's a load of organic material out in the outer solar system. So again, why wouldn't you have life on those bodies? And the interesting thing also from an astrobiology perspective is there's a theory that people can't discount called panspermia, and that is the idea of if life originated on Earth and there would have been giant impacts at that time that life evolved, we have Mars meteorites here on the Earth, and there are probably Earth meteorites on Mars. So there's transfer of material in the Earth-Mars system. Therefore, it is possible that life on Earth could have been seeded by life from Mars or vice versa. It's theoretically possible. Obviously, we don't know if that's true or not. On the other hand, if life evolved in the ocean of Europa, underneath its icy crust, or in the ocean of Enceladus, underneath its icy crust, it's isolated from everything else. So this actually gives us a much better idea of how common is life beyond Earth. So Enceladus. Enceladus is this little tiny moon of Saturn that's been well studied. It was first studied by Voyager, but then studied by the Cassini spacecraft. And Cassini discovered these massive eruption plumes coming out of cracks that are called tiger stripes on Enceladus. So that liquid water ocean on Enceladus actually is spitting itself out into space for us to handily measure. It's very convenient. We're very happy about these plumes. And we've actually flown the Cassini spacecraft, basically on the order of about 40 or so kilometers right through those plumes, and measured the material coming out of the plumes. They're erupting pretty consistently, so we've been able to study them every time we've wanted to. We've been able to fly right through them because they're almost constantly erupting. So what are these things? Basically, this is an artist's depiction, obviously, of what we think is that rocky core inside of Enceladus. We think that rocky core is actually producing some limited amount of volcanism. It's being heated up so much by that tug of Saturn that it's actually creating volcanic vents at the base of the liquid water ocean. All that flexing of the crust is creating cracks as it's being tidally pulled on by Saturn. All that flexing creates cracks. And then the liquid water ocean can erupt or escape out into space through those cracks. Now that story I just told you is bolstered up by those measurements that were made by Cassini. Because what Cassini measured when it flew through those eruption plumes was water, some methane, a nice organic molecule. It measured silicon dioxide, basically little silica particles that must have originally come from that rocky interior of the planet, also suggesting some kind of potential volcanic process. And just a few weeks ago, they announced that they had also been measuring carbon dioxide and a lot of hydrogen. Now that's important because that really does get back to get that kind of combination of gases. it really gets back to the fact that you probably have some kind of what we call hydrothermal vent, or a rock water steam interface that's causing a specific set of chemical reactions that would produce that combination. So we're pretty sure that the scenario you see here is pretty accurate. Now, why is that exciting? Well, some of you might have heard of black smokers or white smokers. These are hydrothermal vents down at the base of Earth's oceans. Extremely rich environments for life. The one odd thing about the measurements from Enceladus is all of this hydrogen, a lot of hydrogen was measured. On Earth, life at those vents actually consumes a lot of the hydrogen, so you don't get a lot of hydrogen going out. So there's a question of, if there's Enceladus life, is it just not consuming the hydrogen? Is there no life there? You know, again, we're basing this how we understand the Earth. Is that relevant? But so that's an interesting point that the scientists are trying to better understand. Again, this was just released about a week ago, or a couple weeks ago. So Europa, it's our other major target out in the outer solar system, moon of Jupiter. Also icy crust, much bigger than Enceladus. So much more like, we think it has actually a much more massive ocean. But similar situation, very large amount of frictional tidal heating caused by the pull of Jupiter on Europa. A lot of flexing of the crust causing all of these amazing cracks. We've learned a lot about Enceladus from the Galileo mission, or sorry, about Europa from the Galileo mission. But it's been our prime target for trying to understand whether or not there could be life in one of these ocean worlds of the outer solar system. Now, about 2 or 3 years ago, using the Hubble telescope, there was the detection of water outside of Europa near the South Pole. And this is the South Polar region of Europa, where you can see there's lots and lots of cracks. And everybody got really excited and said, okay, could Europa, theoretically it should have those eruption plumes like Enceladus does. But the whole time Galileo was in orbit around Jupiter, we never saw any evidence of any kind of eruptions from Europa. We made a lot of observations of it. But there was this Hubble observation that seemed to indicate water plumes coming from the South Pole of Europa. So everybody's really excited. Okay, a much better ocean than Enceladus's ocean, but still kilometers deep. And while we like to talk about submarines that can melt their way through the crust of Europa, that's a bit science fiction. It's technology we don't have. So if the ocean is actually erupting towards us, it makes the whole scientific discovery process much easier. So, of course, what happened was there were skeptics in the scientific community who said, one detection, that's not very good. Galileo never saw them. Are we sure they're there? People did Earth-based observations. Nobody saw the plumes. Well, just about a month ago, there was another paper published that Hubble, they did lots of Hubble observations, more Hubble observations, and indeed they have found additional evidence now of eruption plumes at the South Pole of Europa. So we're pretty sure those plumes are there. So very good news in terms of trying to understand, because we actually already have 2 missions that are planned to go to Europa. There's a European mission called JUICE that'll launch in the 2020s. I think its instrument suite just got final approval. So that mission is moving forward, and it will study not just Europa, but all the other satellites, the Galilean satellites, which are interesting in their own right. And then NASA has been working on a mission called the Europa Clipper that won't go into orbit around Europa. It'll go into orbit around Jupiter, but it'll make multiple close flybys, and it actually has some instruments on board, planned instruments that will confirm the presence of the plumes. Unfortunately, we're not really sure that we can adequately, and the mission's not designed to do it, to actually adequately sample any potential eruption plumes and analyze them. So that's still being worked on. But because of that, NASA has been studying, and it showed up in the recent congressional budget, a lander mission to go in the late 2020s that would actually land right by one of the origin sites of the plumes and wait for material to fall down onto it. Jupiter puts out a huge amount of radiation. So any life as we know it would be, organic molecules would break up from the intense radiation coming from Jupiter on the surface of Europa. So we're worried any life wouldn't last very long. You need a fresh sample to basically really determine if there's life or not. And that's actually why the Europa Clipper, and certainly with JUICE, they don't go into orbit around Europa. Europa's quite close to Jupiter, and the radiation basically fries the spacecraft in fairly short order. And so NASA was putting a lot of technology money into how do you radiation harden all the electronics, and then they decided to go to a less expensive mission that you could get out away from the radiation at parts of its orbit and make the spacecraft last a lot longer. So Jupiter's a very hostile environment to do work in. In terms of going back to Enceladus, we're all, as an international community, getting ready to cry a lot later in the year because the Cassini mission, which has been studying the Saturn system for about 14 years now, we're going to crash it on purpose into Saturn in September of this year. It's running out of fuel, and the spacecraft wasn't sterilized to the degree that we like for planetary protection. That's forward contamination, so we don't want to take Earth bacteria to places where there could potentially be life to confuse us in the solar system. And so we're going to crash the spacecraft into Saturn so that it doesn't accidentally crash into Enceladus, again, where we think there could be life. So that will end our observations. In fact, we will have no more observations from Cassini of Enceladus. But NASA just closed out a new category of mission proposals, and I know there were at least 2 missions to Enceladus proposed. Those missions would fly in like the mid-2020s, so we'll see if any of them make it into the next round, which we don't know yet. The problem with the Cassini instruments is, I didn't mention this when I was talking about the observations at Enceladus, is that the mass spectrometer didn't go out to high enough mass number to actually even confidently identify amino acids. So we know there were organic molecules, we know there were large organic molecules coming out of Enceladus, but we don't know what they were. So you could easily go back with a much more sophisticated instrument and analyze that plume material and get closer to understanding if there were at least very large recognizable organic molecules coming out of Enceladus. Now the other moon of Saturn that I've spent a lot of time working on is Titan. Titan is fascinating because it's actually the only satellite in the solar system with a substantial atmosphere. Its atmosphere is mostly nitrogen, like ours. It's also the only other place in our solar system that has basically a complete hydrologic cycle where it rains, you have rivers and seas, the fluid evaporates back up into the atmosphere, you form clouds, and you have this whole hydrologic cycle. Except it's not really a hydrologic cycle in the strictest sense because it's 92 degrees Kelvin on the surface of Titan. So of course it's not water that's the working fluid in that cycle, it's actually methane and ethane. So it's basically, think of it as liquid gasoline, that's actually a fluid at those temperatures, and it works very well in what we really try to struggle, an alkanologic cycle. I don't know, we tried all kinds of different words. I still call it a hydrologic cycle with methane to try to simplify my life. So really interesting body where we know there's methane being resupplied from the interior of the planet through geologic processes. We know it's being resupplied because incoming solar radiation breaks up methane molecules in the atmosphere over time. So over time, the methane would completely go away, but it's still there, so there's got to be something replenishing it. We think there's methane trapped in water molecules. Water molecules can act like little cages called clathrates, where you have a methane molecule that's basically trapped inside of a water molecule. So we think there are a lot of methane clathrates in the crust of Titan that basically get released, replenish methane in the atmosphere, and keep this cycle going. And so when Cassini got to Titan, it had certainly been proposed at various times that Titan could have liquids on its surface, but it actually wasn't until about 2004, 2005 when the radar instrument that I worked on got its first images of the northern hemisphere of Titan, and this image in the lower left here is a radar mosaic of the northern hemisphere that's been artificially colored. But all of those things you see in dark blue and black are actually seas, with the largest sea being on the order of the size of the Caspian Sea. And from the Huygens descent probe, which was an ESA probe, as it came down more in the equatorial region, we saw these remnants of ancient rivers that you can see there in the upper left that flowed down from higher terrain onto a flat plain. And when the Huygens probe landed on that flat plain, a little puff of methane came out because the ground was probably moist with methane. And we now know from other observations from Cassini and from the the radar and other instruments on Cassini, we've actually seen evidence of rainfall. We've seen the clouds go over, the surface get wet, the surface dry out. So we've actually been able with the Cassini spacecraft to observe these active processes on Titan. So fascinating place to me that you could go, because at heart, as I said, I'm a geologist, but I'm always trying to understand, how does the Earth work? How can we use all these planetary surfaces? And in particular, I tend to study volcanoes around the solar system, but it's always ultimately looking back at this planet and saying, how does this planet work? And when I started working on Cassini, I thought, I'm doing this because it's a radar instrument and I do radar geology. And so it might be fun to do an outer solar system planet. I've never done that before. But I thought, I don't really do ice. What is this? And then all of a sudden, I was doing coastal geomorphology that I hadn't done since I was an undergrad, studying these seas and lakes on Titan and doing things like seeing wave-modified deltas, wave-modified beaches, flooded river valleys. And you thought, I never thought that so far out in the solar system I would be able to study these processes that to date we've only been able to study here on the Earth. So then in about 2006, I got approached by Lockheed Martin Corporation, and they said, we're thinking of putting together a proposal to send a boat to a sea on Titan, and we think we can do it in the Discovery mission category, which was $425 million at the time. And I laughed, and I said, that's not possible. And they said, no, give us a chance. We think it might be possible. Give us a chance. Don't you want to lead the proposal? I'm like, why don't you get these other people? And they said, no, we want you to do it. So I ended up leading this proposal that we called the Titan Mare Explorer, and that's a little Mare is sea, a proposal that we put in to NASA. And we did kind of an introductory proposal. It got funded. And I thought, well, this is interesting. But at that point, the Jet Propulsion Laboratory, which does most of the planetary mission studies for NASA, they had done something they called the $1 billion box study. And they basically said, is there anything that you can do in the outer solar system for under $1 billion? And the answer they came back with was no, definitely not. So I was a little skeptical, and a lot of the community was really skeptical. So we ended up putting in the Discovery proposal, and there were about 28 proposals that went in, and they down-selected to 3. And we were one of the 3. And I was shocked by this, partially because I never win anything. Like, stand next to me in a lottery ticket line, I'm guaranteed to lose. So I'd never won anything, so it was very exciting. What you do at that point, you go into something that's called Phase A. They give you a certain amount of money, and you basically have 7 or 8 months to flesh out your proposal so that they can see, is this really technically feasible or not. So we partnered, at that point we'd already partnered with the Applied Physics Lab of Johns Hopkins University, and we started to work on this proposal, and it was incredibly fun because you're really starting from scratch and saying, okay, how can I fit in this cost box? I know I'm going to land in a sea. What can I do? What can I measure? What can I afford? Can I have a sail? No. Can I have a motor? No, too expensive. I just wanted a sea anchor so we wouldn't bobble as much. I didn't even get my sea anchor. We had to do direct-to-Earth communication because we couldn't afford an orbiting satellite. So while bobbing on the sea, which we had to figure out how much are we actually going to rock, which we did with all kinds of sophisticated models based on a small amount of data, where are we going to go when we land on the sea? We were aiming for this sea at the time, was the only one we had mapped large enough to land in. It's called Ligeia. And those crazy lines you see are using the best global circulation models of the atmosphere that we had at the time. We ran all these plots to say, okay, if you plop down in the middle of your landing ellipse in the middle of the sea, in 3 months, where will you go? The wind does blow on Titan. It has a very dense atmosphere. So you actually make tracks. You know, our big fear is, what if within a week we washed up on the beach and sat there for 2 months? Still great science, you know, so you have to write this proposal. You have to figure all this stuff out, basically literally from first principles. And when I mean first principles, I mean first principles. How do you land in a sea made of methane and ethane? How do you splash down? What are the properties of the liquid? Can we convince the reviewers that we can do this? Anyway, so we worked on it for all this time, and we ended up losing to a mission to Mars called the InSight that's been now delayed till 2020. It was supposed to launch this past year, but it's been delayed because of problems with the chamber that holds the seismometer. So we ended up losing, mostly because our mission and the other, one of the down-selected missions of the 3, our 2 missions used a new technology called an advanced Stirling radioisotope generator. So it used a Stirling system powered basically by plutonium, not the bad kind of plutonium, the benign kind of plutonium, to provide heat, which kept our instruments warm inside the spacecraft, but it also provided power. That technology ended up being behind schedule and over budget. It got canceled. The whole program got canceled after they didn't select our mission. So it was hugely disappointing. And it's disappointing beyond that because Titan's axis is inclined like the Earth's axis. So like the Earth, its north pole goes dark in Titan winter. The problem is Saturn and Titan have a 17-year seasonal cycle. So it will go dark at the North Pole in about 2026, 2027, and it'll stay dark until the early 2030s. Now that's bad if you're me, like a geologist, you want to go somewhere, you don't really want to go in the dark. But the other problem is I told you we did direct to Earth communication. And the problem is when the sun sets, the Earth sets also. And so the mission actually can't be proposed again until the mid-2030s. And by that point, I'll be too old. It was hugely disappointing, but about 3 weeks later, or no, it was actually about 4 months later, I got a call and they said, do you want to interview to be chief scientist of NASA? And I said, well, okay, I'm still mad about that Titan mission thing, but okay. So hugely disappointing. I will say there's at least 2 Titan missions that have gone into this mission selection call that NASA will ultimately make the decision sometime this fall for what missions will be in the down select. There's at least 2 Titan missions going in. None of them are boats to the sea. They're more equatorial missions, but they're exciting missions. One of the things that's so interesting, back to why, obviously we wanted to understand these Earth-like processes. How do waves get generated? How does a non-Earth ocean, what's that air-sea interface, the exchange of gases? How does it control the weather? What's the climate? So this whole idea of being able to go to an alien sea and try to understand these processes that we've only been able to study on this planet was fascinating. But back to the search for life. All right, it was also interesting. You have a fluid, you have a load of organic material, but there's no water, and it's cold, cold, cold. And chemical reactions proceed very slowly at cold temperatures. So could you have life? Could you have weird Titan life fish stuff? You know, obviously we don't know. And we were sending a fairly sophisticated mass spectrometer. We had a camera on board. And to be honest with you, a lot of what we were going to be looking for was this idea of disequilibria. Could we find an excess of something and a deficit of something else that would tell you maybe there's an active process going on? Could we assess what it was? Could it be life? So Titan's kind of this outlier of saying not just life, but how much are Earth-like conditions important to the evolution of life? And so that's why I think ultimately, obviously, we are going to go back to these seas, but I think they do hold clues about the limitations of life beyond Earth. Wow, okay, I better hurry up. So Mars, obviously you guys know Mars is the focus. As I said earlier, Mars had water on its surface for on the order of 1 billion years. We know from our studies of the Curiosity rover and Gale crater that Mars had running water on its surface. There's huge questions that we still have of how did the atmosphere get dense enough and warm enough to keep running water on the surface, but there's clear evidence from Gale crater that those were the conditions. We have found fragments of organic molecules on the surface. The problem is Mars lost its magnetic field fairly early in its history. Again, incoming solar radiation breaks up organic molecules. So think of taking a puzzle piece and ripping it to shreds. That's what we're kind of finding in terms of organic molecules on the surface of Mars. So Mars lost its water, became cold, its atmosphere thinned about 3 billion years ago. So if there had been life on Mars, it either went extinct or retreated underground. Now, the other problem is, if you go back to thinking about life on Earth, I talked about how life evolved very rapidly here on Earth once conditions stabilized. But even after 1 billion years, if you look back to about 2.5 billion years ago, 3 billion years ago, we're still talking single-celled organisms. We're not talking about anything with any complexity. So when we talk about life on Mars, we're expecting basically single-cell kind of microbacteria type stuff. So it's a disappointment for people who I think we're going to find, fossils well, I see on the internet all the time people see dinosaur fossils in our Curiosity images. It's not true, because really we don't expect much beyond fossil microbes. But it's really got the astrobiology community thinking in terms of how do you identify life? Is life going to be easy to identify and easy to understand? And so they've actually created something that's way more complex than I'm showing here, called the ladder of life, which goes through things like, are there general indicators? The first one is habitability. Was there liquid water on the surface? But then general indicators. Do the molecules show a chirality, which is basically molecules have a left and a right hand. Life molecules favor one. So do we see that kind of pattern of molecules on another planet? Potential biomolecule planets or components, looking for things like amino acids, looking for things like lipids. Functional molecules, can we identify DNA? Can we identify RNA? Of course, we don't know that life on another planet would have evolved in the same way that it did on Earth. If it's extant life, living life, can we see evidence of metabolism? Can we look at isotopes to see evidence for metabolism? If we find extant life, does it show, can we identify that it is actually life by seeing growth, by seeing reproduction? And ultimately, the test of life, and part of the definition of life, is does it exhibit Darwinian evolution? So the scientific community is really working on how do we identify life? How can we convince everyone else in the scientific community that we're actually seeing something that is evidence of life? So when we go through all that, many of us in the community have come to the point we're going to need an awful lot of samples. One sample, one small sample from the surface of Mars is never going to convince us that there's life on Mars. So how are we ultimately going to answer this question? I actually think it's going to take geologists on the surface of Mars breaking open a lot of rocks, looking at a lot of samples, because you just don't need one fossil, because one fossil, oh, is that really a fossil? Is it not? You're going to need a lot. So it's going to take humans who are creative, who can move fast. Our Opportunity rover has been on Mars for over a decade. It's gone about 27 miles. Humans, not me, can go that fast, obviously, in hours. So we do need humans on Mars. So NASA has a plan to get humans to Mars orbit by the early 2030s. We are working very closely with all our international partner space agencies. The plan is to finish the work we're doing on the International Space Station, put basically a practice Mars transfer vehicle in orbit around the moon in the mid-2020s, and then get to Mars orbit by the early 2030s and to the Mars surface by the late 2030s. Why that long? Because Mars is hard. You're exposed to radiation on the way there. Microgravity debilitates humans. That's what we've been working on to counteract that on the International Space Station. There's a huge time delay at Mars, up to an hour round trip. Your family says hello to you, you hear it a half hour later, an hour later they hear you say, what? All right, psychologically, that's tough. How do we deal with that? How do we land large amounts of mass that humans would need on the surface of Mars with its very thin atmosphere? We're working with SpaceX, which has been working on supersonic retropropulsion, which is basically what we're going to need. So we're partnering, NASA's partnering with SpaceX on something called Red Dragon, where they're going to send one of their Dragon capsules to Mars. So lots of technology work to be done to make sure we can get humans there and then safely home again. Again, very international effort from our next uncrewed mission, which is the Mars 2020 rover, which has great international participation. Europe is planning in 2020 the ExoMars rover, which will further the search for life on the surface of Mars. And then as part of the effort to get humans to Mars, Europe is providing the service module for the Space Launch System, which you see there in the bottom right, which is part of the rocket system that will help move humans beyond low Earth orbit. I had put this image in my talk a couple weeks ago that I gave, and somebody from the AV people said, oh, that image is really bad and pixely. Are you sure you want to use it? The reason this image is so bad and pixely is actually this is the Earth-Moon system as taken by one of our Mars orbiters. So this is, with a good telescope, the view that someday those humans on the surface of Mars will be able to see of our own planetary system. And to me, it always brings me back to the fact that as the sign I held up in the climate march a week ago said, there is no planet B. You know, when we go out and we search for these habitable planets around other worlds, there's still no alternative for humans to this planet. And so in terms of understanding, for example, the role of greenhouse gases in planetary atmospheres, this whole issue of comparative planetology, how do we better understand our own planet by looking at others, has certainly been informed by our study of other worlds. And obviously, as you well know, and we know from these data, and obviously you can find from any of the other space and weather agencies around the world, similar data which obviously says that the Earth is warming and is warming at an alarming rate. And I had just seen the first 3 months of 2017 have been even hotter. And then obviously if we look at the effects of that are occurring right now, and I like to talk to audiences, especially in the United States, about this, is that we see the effects of climate change right now, because a lot of people have this idea that climate change is something abstract that happens in the future. And you're like, no, we see Greenland melting, we see that from European Cryosat, we see it from our ice bridge aircraft that goes and studies Greenland. We see huge melting in Western Antarctica. I think it was actually the British Antarctic Survey that took this picture of the crack in the Larsen C ice shelf, where we're seeing a lot of melting and collapse of the ice shelves that hold the ice onto the Antarctic continent. That's bad news because the IPCC original reports didn't entirely incorporate the melting because it just wasn't well understood how much melting was going on in Greenland and in Western Antarctica. And then of course you see the effects in places like Miami Beach in the United States, where they are raising roads and installing pump systems because they're getting so much regular flooding now at high tide, or at king tides. Through there's been a series of data that have been put out, and these are some data that NASA put out called the Global Daily Downscaled Projections through a system called the NASA Earth Exchange, where they used all the climate models that have been put together from various countries in a project called the Coupled Model Intercomparison Project, or CMIP. This is from CMIP 5. And in this scenario, which obviously is July of 2099, so Northern Hemisphere summer, this uses a scenario out of the International Panel on Climate Change report, which is called RCP 8.5, but you can think of it as business as usual. This is the this is the track we're on. It's not the let's keep it at 2 degrees centigrade. This is like, okay, we continue where we are. These are the temperatures that we're potentially going to be seeing out at that time period. And if you think of where we grow food to feed what at that point will likely be on the order of 9 billion people, you can see that we're in real trouble if we don't change our ways. The good news is we have these models. We know what is potentially going to happen. And we're already taking this extensive Earth observation data that's collected by space agencies all around the world and trying to help communities around the world become more climate resilient. And this is important because some of the effects of climate change are going to occur no matter what we do about carbon emissions, such as some amount of sea level rise and certainly more severe weather. So NASA has a program called SERVIR where we work with the US Agency for International Development. We have hubs around the world where we go into countries in Africa, in Indonesia, the Mekong Delta region, and we say, here's Earth observation data that can help you with your issues. And for example, in Bangladesh, they've actually increased flood forecasting up by the order of a week, which is obviously saving lives around the world. I think all of the astronauts, when they come back from the International Space Station, they have this incredible feeling about trying to protect this planet because this is the view, that they get to see of the planet. All of us, when we look up, we see this massive atmosphere. They see this very, very thin atmosphere over this very large planet, and it leaves them with an intense feeling of the importance of protecting this planet that we live on. So thank you very much, and I'm happy to take questions if we still have time.
I wish I could go back 40 years and think about science or anything else, but you ended with a very spectacular example of why the data, the information that NASA and other agencies are collecting is so important to help us understand where we are now. But you also talked about some of the fascinating work that you have planned, have implemented across space in finding data. And there must be as many different approaches to questions as there are people in the audience. So we have about 20 minutes, and I'm going to ask you all to be incredibly disciplined and not give us lectures before you ask your questions, but just ask your questions if you could. We've got 2 mics. Would you like to take a question at a time, or should we take 2 or 3?
At my age, I think a question at a time.
Okay, first question.
Even 2-part questions get me muddled at this point.
Right at the back in the middle, and can we try and get...
That's okay, I think it's a great auditorium, and you should be able to hear me.
Okay, I'll repeat the question for the people that might be in the other room. Yeah.
It was a wonderful lecture, great vaulted ideas, and bringing us back to Earth with the Anthropocene. So, staying with that for a moment, and staying with the second word of your title, which is international. How international are these programs? You mentioned a number of countries. You missed out China. Why are we not collaborating with China? What are they doing?
Okay, so great question about international.
It's a great question about international collaboration and specifically with China. So as I said, for example, just to start with Earth observations, there's a committee, there's a group called the CEOS, it's the Committee on Earth Observation Satellites, that's got complete international membership, including China. There's a group called the Global Exploration Roadmap that you can Google and you can download. That's for human exploration, and China is a member of the Global Exploration Roadmap team. In the US, NASA has been put in an extremely awkward position because the Congress of the United States has banned NASA from bilateral working bilaterally with China. The previous head of the House Appropriations Committee really didn't like China, and so he wrote it into US law. He retired. The next person who came in reiterated the policy. So NASA, I mean, we talk to China when it's like satellite avoidance. We've been doing a little bit, talking about some Earth work, but in general, NASA doesn't. That's not to say other space agencies don't. The European Space Agency talks to China, the Russian Space Agency. So basically everybody but the US talks to China. Now, obviously, China has been going with leaps and bounds. They have a space station that they're beginning to put up. I think their space station is supposed to be up around 2020. They have sent a probe to the moon. They've been talking about sending humans to the moon. They've been talking about sending humans to Mars. So they have an extremely active space program, and I will say most of the space agencies of the world are talking to them in a multilateral sense. They are part of these multilateral dialogues about Earth observations, about human exploration. It's just NASA is not allowed to have bilateral. And I will say the previous head of NASA, who was my boss, Charlie Bolden, was very vocal about the fact that he did not like this restriction, and he felt like that NASA was being left behind the rest of the world. The rest of the world's collaborating with China. Why isn't the US?
Next question. Okay, this is going to be interesting. Can I take one right in the middle there, please?
Thank you, Dr. Stofan. Fascinating talk. There were a few papers by a Hungarian group, a company, in around about 2005, suggesting that dark dune spots in the poles of Mars were behaving like photosynthetic microorganisms, or colonies of. Does NASA have a view on that, or has it sort of disappeared into an inorganic thing again?
I haven't seen anybody talking about that. I remember when it came out, and I haven't heard anything about it since, so I think there's been no kind of consensus that that could be true. NASA's even gone through, a couple years ago, we announced evidence of liquid water on the surface through what are called RSLs, or recurring slope lineae, which are basically sort of cracks that come down the edge of some craters and some steep faces. We saw them apparently wetting and drying. Even that has now been by other US scientists that, it may not actually be liquid water, so maybe that's not wrong. So these things are generally pretty hotly debated in the scientific community, and I haven't seen much on that since then. And frankly, that's part of the reason that I actually think it's going to take humans on the surface of Mars and this massive amount of samples to ever prove life, because unlike what you hear especially about climate science, the scientific community, we actually don't like to agree with each other. We like to just prove each other wrong all the time. And the idea that the scientific community is like trying to help each other, no. We love to cut each other off at the knees. In a nice way, of course, collegial, constructive kind of way, mostly.
I think it was Stephen Hawking who said a while back that this Earth will become uninhabitable in 100 years, and the only future for mankind is to leave Earth and find somewhere else. Do you subscribe to that view?
I don't at all. And in fact, I spoke at the big science march in DC a couple weeks ago, and there was a school teacher there, and she said when she tried to talk to her students about climate change, she said that they said to her, we don't have to worry about that. We can go to another planet. And she was really upset about it. And this was a little talk we were doing. I was doing it with two other planetary scientists where we were talking about how planets help us understand climate. And we were all horrified. And obviously, Mars is hard. So sending people there is something that's extremely hard to do. When we talk about sending humans to Mars, it makes Antarctica look like a walk in the park. And so when we talk, a lot of people like to talk about Mars, settlement. I don't think that's going to happen for centuries, because, think of humans going to Mars much more in an Antarctica mode. You're going to have small international bases focused on scientific research. This isn't a place with shopping malls and hotels. It's too hard, it's too far away, it's too dangerous. So the idea that there is a planet B, that we can just kind of throw up our hands and say the Earth is going to be uninhabitable, to me, the answer to that is no. We have a problem in front of us. We've got to do something about it. I think that's our only choice. And it upsets me because I think it gives people an out, almost like, oh, we don't have to worry about that. It's going to get fixed. Well, no, it's not. It's on us.
Okay, please.
Dr. Stofan, thank you very much indeed. You expressed an interest in Venus. You've studied Venus considerably in your career. Is Venus just completely too hard for any real research to go into it?
I was looking for Colin, but he left.
The reason I ask that is that surely Venus is a real warning sign for us here on Earth.
Yeah, and so the questions about Venus and the exploration of Venus, is it too hard, and Venus being a warning sign. When I started working on the Magellan mission, it was 1989, and so I was giving talks, public talks about Venus and its runaway greenhouse in 1990, 1991. And I used to say to audiences, at that point, I would explain the potential for global warming, talk about the role of greenhouse gases in planetary atmospheres, and I would say, look, at this point, the models aren't totally in line, but is this something that we want to mess with? Because once we start down that path, it's going to be hard to get off of it. And obviously, in fairly short order, the model's hugely improved, the model's aligned, and we're on the world we see now. And so I think that Venus is a huge warning, but Venus is actually an also really interesting place to go to study some of the aspects of climate. For example, the role of aerosols or small particles in atmospheres, the role of clouds in atmospheres. There's huge things we can learn about Venus by going back. And obviously we've had a spacecraft at Venus for the last number of years, the Venus Express spacecraft, which is an ESA spacecraft. A number of Venus missions have been proposed to NASA. They keep getting turned down. A lot of the times there's technology and cost reasons. Venus, it's hard to get down to the surface. We need to make all kinds of atmospheric isotopic measurements to understand the history of water on Venus. 900 degrees Fahrenheit on the surface, it's a challenge. But come on, the Russians landed on, the Soviets landed on Venus in the early 1980s. This isn't like, we can do it. And so it's very frustrating to the Venus community because for those of you who've seen Galaxy Quest, I say the Venus community is the Galaxy Quest of planetary scientists. Never give up, never surrender. Because we'll keep proposing missions. Sooner or later, one of them will get selected. Because Venus has an awful lot to tell us about that question of how do you get and maintain a habitable planet, and how do we understand greenhouse atmospheres? So we'll get back eventually. And again, out of Oxford, Colin Wilson here has been working on a Venus mission proposal for ESA. That's quite a good mission.
What's your question? Just that.
I shall ask that you
Okay. I'm looking around.
Since you mentioned on your boat going to Titan...
My boat not going to Titan.
like plutonium as a fuel source, is there anything going on at NASA for future missions with alternative fuel sources?
Yeah, so right now, one of the main power sources, so obviously you have a limited number of power sources that you can have for planetary spacecraft, and most of them have solar power. But obviously way out in the solar system that becomes problematic. The Europa Clipper is actually a solar-powered mission, and that's about the limit of what we think we can do to power a mission that far out. Anything further out, and in general, any mission uses something called RTGs, which are basically powered by small amounts of plutonium. They're radiothermal generators. The ASRGs were a way to use less plutonium and get a lot more power because the Stirling cycle is a very efficient cycle. So they are still looking at the technology. We got the program at least to the point where they're trying to figure out, can we actually get this into a viable system? Because again, it uses less plutonium, gives you more power. They're also working on, and it's being offered, I think in the New Frontiers call, they were offering the use of 2 MMRTG, which is something called a multi-mission radiothermal generator, which gives you a little more power. It's a little bigger, it's a little bulkier, but you can still use it. So those are another power system. that's available. And Europe has been looking at some alternative fuel sources, and I don't know where that is right now for a Stirling cycle or an RTG.
So, thank you for a fantastic lecture. You emphasised quite a lot the organic molecules, amino acids and methanes and ethanes and so forth. I wonder whether or not NASA has also thought about non-carbon based reproduction systems and based on other molecules, for example, silicon technology or any other molecule.
It's been thought about, and in fact, there was a big, I don't know what to term it, a big thing a few years ago when there was a NASA-funded scientist who thought she'd found some arsenic-based life in California. It turned out maybe not, so that was a bit controversial. But everybody's certainly looking for it on this planet. You know, is there any evidence we can find on this planet? And then certainly, I think that's one of the issues. And in the ladder of life, you know, that I talked about, which again, if you go to the NASA's astrobiology website where they lay it out, you know, that's one of the basic issues is, are we actually going to find, are there other, you know, people talk for Venus, for example, could you have sulfur-based life, not carbon-based life? And I tend to think we know almost nothing. And that there are potentially many forms of life out there, we just need to go discover them. And that's why, to me, while Europa, Enceladus, Mars are all fascinating, we need to go do it. But I love the Titans and, you know, even my friend David Grinspan's theory about life in the clouds of Venus, because that to me is, what are the possibilities of life, and are we looking into narrower of a range? And we won't know until we go find out.
You've not mentioned at all the various projects looking for any radio signals coming from space or these other things. Is that because you think they're not a good use of time, or that's because they're not what NASA do?
It's mostly because none of the space agencies around the world do that. So NASA at one point did fund SETI, the Search for Extraterrestrial Intelligence, where, you know, the basic concept for those who don't know is you put big antennas out there and you look for radio signals coming from another planet, with the idea that we here on Earth, you know, unfortunately we're sending out, you know, Survivor and, you know, the X whatever, you know, all these TV shows, you know, we're sending all that electromagnetic noise out, and God knows what other civilizations think of us. That's probably why they haven't contacted us. You know, so we admit so much. So wouldn't other planets be doing the same? Okay, so right there, that's an assumption. Do they communicate and make the same kind of noise we make? Maybe, maybe not. But right there, that's an assumption. You know, I think it's worth doing. It's not a huge amount of effort, and so I'm glad that SETI is doing what they're doing. They've got private funding. More power to them. If they find something, great. I'm probably a skeptic, and the part that I didn't talk about in the Drake equation is the part where it says, how does a society get to be, you know, do you get complex life forms? Do you get intelligent life? And I'm probably more skeptical on that side. When you think of how long, that chart I showed, when you think of how long it took to get complex life here on this planet, us, it took billions of years. And when you think how close life came on this planet to being wiped out multiple times by asteroid impacts, you need stable conditions over long periods of time for life to evolve to the point of complexity. Then you look at how hard we're trying to wipe ourselves out. And you're like, and we don't even have the technology slightly to get much beyond the limits of our own solar system. Whenever I talk to kids, I'm like, one of you has to invent warp drives, so get to work. You know, I guess I'm more skeptical. Not to be a downer.
I've probably got time for 2 more questions, so think appropriately. One here.
Thank you. I wanted to ask, what would be your comment for searching for extrasolar life, even with the biggest telescopes? Can we somehow detect spectroscopic signals for extrasolar planets harboring life?
Well, you know, as I talked about in the beginning, the first step is to really, and when I showed that really complex chart that Vicki Meadows is doing, and her group is doing a lot of work on, and as are multiple groups around the world, doing groups to say, what would I look for in a spectroscopic signal? And I talked about this disequilibria of gases that you might start looking for and then saying, can I attribute that to some process? But again, that's, you know, that's a lot of ifs change together. Where I think we're going to make huge breakthroughs is when we can image extrasolar planets, because one of the things in the ladder of life is pigmentation. Life has color on this planet, and we assume life will have color on other planets. So when you think of things when the Earth was dominated by blue-green algae, we would have been able to see that. If you think now, you can watch on the Earth from space and from other planets, the planet turn green and then brown, and so you can watch the colors of life on this planet. So to me, once we get to the technology when we can have fairly decent resolution images of a planet, enough to maybe see those color pigmentation changes, it still could be geology, but then you start saying, okay, maybe it could be life, and you get a little further, you know, down that line of reasoning. But the real problem to me is these places are so far away that our chances of actually getting confirmation is very difficult. So.
One final question.
So you talk very eloquently of linking this. I mean, it's absolutely fascinating. Come as a complete buffoon to this. And you shift it into the significance around climate change. And what your last slide showed is we're not sure if there's intelligence life on Earth.
I didn't say that, you said it.
Yeah, I know. So, I think one serious question, one frivolous question. One is, you mentioned about the link into Lockheed Martin. All the front page news of exploration, space exploration now is the kind of Elon Musk, let's get up into space, let's fly rich people around, and maybe some of them crash. But what you're showing there is that there is a real solid body of science that is going on, which doesn't hit the front page. And how frustrating is that? And how much do you think the whole idea of the exploration of life is being dominated now by this kind of private sector stuff? The more frivolous question is, what do you guys say when you really want to say this isn't rocket science?
We still say that, but it never comes off very well. I thought you were going to get asked. I got asked in a well, I was on a panel for NASA that was a Search for Life in the Universe kind of press conference-y panel we did. And so someone from Twitter or something asked a question, is NASA concealing life that they've already found? And so the guy that was head of space science at the time, this guy John Grunsfeld, who fixed Hubble 5 times, he's like this amazing guy. He's like, I think that's a question for our chief scientist. So I make a face, forgetting that I'm actually on TV. You know, I'm like, I literally did that. And then I answered like, of course, we would tell everybody, you know, I didn't say the obvious question, our funding would triple if we found life somewhere else. So, you know, I'm like, of course we would go find it. So some guy in the internet made a conspiracy video that the face I made was proof that NASA was covering up. Plus I waved my hands when I talked. So that was also proof, because people who wave their hands are lying. So sorry for all my lying. To your serious question, I think my main frustration, because for me, while we talk about exploration and going to Mars, and I was on a panel last night with Andy Weir, who wrote The Martian, which I loved, but you know, it frustrated me in The Martian that they never talked about why we were going to Mars. And obviously a lot of the public doesn't care why we're going to Mars, but to me it's this fundamental question of we're going to understand more about the origins of life if we go to Mars. And how can you not talk about that? Because the public would get excited about it. But in general, I have found that the public gets extremely excited about the idea of sending humans beyond this planet. And I really do think to some extent it is in human nature to want to know what's over the next hill. And right now, what's over the next hill is Mars. And so I think the exploration part gets a lot of press, and we do collaborate, with companies like SpaceX, companies like Lockheed Martin to get there. And I think the public is really intrigued, obviously, by Elon Musk being this kind of, independent figure who's really helped bring prices down and who collaborates with NASA a lot. He's, his company's been great. But I get more frustrated that I can get up and talk to the public about most of the stuff I talked to you about tonight, and they're willing to totally believe everything I say. I talk about climate change, and they're willing to tell me I'm wrong. And I'm like, okay, really? And so that's probably my big frustration is why have climate scientists become experts that a lot of people think are no more informed on climate science than they are, even though, my husband's an investment guy, so I'm not gonna, he totally understands climate change. But, I've had investment people tell me I'm absolutely wrong about climate change. And, you get to the point where you're like, I have a PhD in planetary science, you don't. Okay, that's not a valid argument, I realize. But it's very frustrating as to why has the science been so difficult to get across? And obviously there are huge reasons for that, not the least of which there's been an active effort, especially in the United States, by fossil fuel companies to spread misinformation, which has confused the public. But I think, on a variety of issues, that public understanding of science, public, when you have a situation like climate change that is literally a threat to the human species, and you have people saying it's not true with misinformation, it's just very frustrating for the science community. And there's great people, including people here at Oxford, who've done a lot to try to communicate the science and who are really getting the good science out there. We just need to listen. And again, this is way more a problem in the US than it is here. So thank you.
Thank you. Can I just say that that's a wonderfully, typically thoughtful point at which to bring this evening to an end. That we need, all of us, not just to try to understand the science, but to be prepared to believe the science and to question the science and make sure we do understand it and then communicate the science. And I think this evening we've had a wonderful example of what happens when an inspirational, if I may say so, female chief scientist, thinking about the question balance, that is able to stand up and explain science in a way that engages and delights and excites. So we're very grateful for your speech this evening.
Thank you.